10.4 Lesson 2, Polar Coordinates and Polar Graphs. Our objectives for today are 1. You'll be able to graph polar equations. 2. You'll be able to convert a rectangular equation into a polar equation. And 3. You'll be able to convert a polar equation into a rectangular equation. These are the vocabulary terms that we looked at in Lesson 1 as we started with the polar coordinate system. For Objective 1, some polar equations are really easy to graph. For example, you have r is equal to 2. Remember that polar coordinates have r and theta, where theta is the directed angle from the polar axis, and r is the directed distance from the pole. So if you have a polar equation such as r is equal to 2, you'll notice that there is no theta there. So what that means is, because we don't have theta, theta can be any angle. But what has to be the case is that for any given angle, the distance from the pole must be exactly 2. So theta can be any angle, but the distance from the pole for any angle must be exactly 2 units. So if the angle theta is 0 radians, then you'll have this point here. If the angle theta is pi over 6 radians, you'll have this point here. If the angle theta is pi over 3 radians, you'll have the point that I just marked. If the angle theta is pi over 2 radians, you'll have this point. If the angle is 2 pi over 3, you'll have this point, 5 pi over 6. So no matter what the angle is, on the terminal side of the angle, you will locate a point that is 2 units from the pole, and of course you have a set of points that are equidistant from the pole. So what you have is a circle with the pole being the center and the radius being 2 units. So that was really easy to graph. Here's our second example. In our first example, we had r is equal to 2, and theta could have been any angle. In this example, we have theta is equal to pi over 3. There is no r in this equation, so r can be any value. You can have a directed distance that's positive or negative or 0. But the angle has to be fixed. So the angle of rotation from the polar axis is pi over 3 radians. So we locate pi over 3, the radial line pi over 3. This would be the radial line pi over 3. And of course, the radial line will also go in the opposite direction. So this is the radial line pi over 3. So we'll say that this is the radial line, just looking at the terminal side of the angle. Theta is equal to pi over 3. But because r can be any value, you can have r is equal to 0 and you'd have a point at the pole. You can have r is equal to 1 and you'd have this point along the terminal side of the angle. You can have r is equal to 2, r is equal to 3, r is equal to 4, r is equal to 5, r is equal to 6. And you can also have negative values for r, because r is the directed distance from the pole. So if you have r is negative 2, then you'll have this point here. If you have r is negative 4, you'll have this point. Because if r is negative, you're looking for points that are a certain number of units from the pole on the ray that is opposite the terminal side of the angle pi over 3. So if r is equal to negative 6, you'll have this point. If r is equal to negative 5, if r is equal to negative 3 and negative 1, and so on. So these are the set of points that we have. When you connect them with a smooth curve, you get a line. So the graph of theta is equal to pi over 3 is the red line that you see there, and that was also pretty easy to do. Sometimes you'll have a problem like this, graph r is equal to secant theta, and it's not as easy to do as the other two that we've seen. And in some cases, it may be a lot easier to graph the polar equation by converting it into a rectangular equation first. And that is the case for this particular example. To convert our polar equation into a rectangular equation, we can look at the coordinate conversion equations. Now, you may remember from trigonometry that secant is the reciprocal of cosine. This is a reciprocal identity. Secant of theta is equal to 1 over cosine of theta. And one thing that you will notice is that if you look at this particular conversion equation, x is equal to r times cosine theta. So if I multiply both sides of this equation by cosine theta, then I would get, on the right side, if I multiply by cosine theta, I would have 1. And on the left side, if I multiply by cosine theta, I'll have r times cosine theta. But what is r times cosine theta? R times cosine theta is x. So I can replace r times cosine theta with x, and I just have the rectangular equation x is equal to 1, which is very easy to graph. Remember, we superimposed the rectangular coordinate plane with the polar plane. And here we have the x-axis, here we have the y-axis. This would be x is equal to 1, this would be x is equal to 2, x is equal to 3, and so on. This would be y is equal to 1, y is equal to 2, y is equal to 3, and so on. So when you have the rectangular equation x is equal to 1, there's no y in this equation, so y can be any coordinate, but x always has to be 1. So you get a set of points along this vertical line, and all of these points that I'm showing with green, they all have an x coordinate of 1. So the graph of the polar equation is a vertical line. It is the graph of x is equal to 1. In this problem, we were able to graph the polar equation easily by first converting it to a rectangular equation. And our lesson for today is about converting polar equations into rectangular equations and rectangular equations to polar equations. And we'll look at some examples after the next graphing example. Suppose you want to graph the polar equation r is equal to 5 times cosine theta. It's not quite as easy as the other ones that we've seen. And you could certainly turn this into a rectangular equation, and it would be easier to graph as a rectangular equation. The graph will be a circle, and we'll take a look at how to convert this into a rectangular equation in one of the examples that follows. This would be the polar equation for number 38, and we will convert it into a rectangular equation in one of the examples that follows, and the graph will be a circle, which is easy to see after you've converted this polar equation into a rectangular equation. But I do want to go ahead and discuss how you can also graph it directly from polar form, in addition to converting it into a rectangular equation. In this case, that's actually easier to do. But if you wanted to graph it not by converting it into a rectangular equation, but directly from polar form, you can do that as well. What you'd have to do is make a table of values. So you'd have input values would be theta, and output values would be r. And you would choose different values for theta, like 0. Cosine of 0 is 1. 5 times 1 is 5. You can also try something like pi over 3. Cosine of pi over 3 is 1/2. 5 times 1/2 is 2.5. You can try pi over 2. Cosine of pi over 2 is 0. 5 times 0 is 0. You can try 2 pi over 3. Cosine of 2 pi over 3 is negative 1/2. 5 times negative 1/2 is negative 2.5. You can try pi. Cosine of pi is negative 1. 5 times -1 is -5. So let's take a look at plotting these points. So if you have an angle of rotation that's 0 radians, then the terminal side of the angle will be along the polar axis. So now you want to locate a point that's 5 units from the pole on the polar axis. So that would be right here. So this is the point 0, 5. Now you have an angle of rotation that's pi over 3 radians, and then you have r that's equal to 2.5. So here's the radial line, pi over 3, and r is equal to 2.5. So we locate a point that's 2.5 units from the pole along this radial line right here. So we have 2 points, and then the angle of rotation that we looked at next is pi over 2 radians. So here's the radial line, pi over 2, and r is equal to 0. So we would have this point here. And then we have 2 pi over 3 is the radial line. So we have 2 pi over 3, which would be right here. And you'll notice that r is negative 2.5. So we have to locate a point that is on the opposite ray from the radial line, from the terminal side of the angle, and 2.5 units from the pole. So that would be right here. And then we also have pi and -5. So here's the radial line for the angle of rotation pi. And because r is -5, we have to locate a point 5 units away from the pole on the opposite ray. So we get the same point that we had earlier. Now you'd probably want to fill in with additional values for theta, such as pi over 6 between 0 and pi over 3, and maybe 5 pi over 6 between 2 pi over 3 and pi. That might help you see that what you have here is a circle. So cosine of pi over 6 is square root of 3 over 2, and then you multiply that by 5. That gives you approximately 4.3. So you have pi over 6, and you locate a point that's 4.3 units from the pole along that radial line. It would be about here. And you can even do pi over 4. You can do pi over 4. Here's the radial line, pi over 4. And we need to find cosine of pi over 4 and multiply by 5. So when theta is pi over 4, you get an r value that's about 3.5. So I'll locate a point that's 3.5 units from the pole. And this is what I have. So you can see that I have these points, and I start here at theta is equal to 0, and this is how my curve is traced. And what I have is a circle, and of course you can get additional points here. I didn't do that. But what I have here is a circle. It is centered at the point that I'm marking here. And the radius of this circle is half of 5, or 2.5 units. So that's one way you can graph a polar equation. You can make a table of values. You can convert it into a rectangular equation and graph it from the rectangular equation. We will see that in an example to follow. An alternative way you can graph it is to convert the polar equation into a set of parametric equations and then make a table and graph the set of parametric equations. If you wanted to take that approach, you have r is equal to 5 times cosine theta. So you have x is equal to r times cosine theta. So you will have 5 times cosine theta times cosine theta, and you will have y is equal to r times sine theta. So you'll have 5 times cosine theta times sine theta. And if you do it that way, you're going to make a table. The parameter that you have would be theta, and you'll make a table with a row for x and a row for y, and you will choose values for theta, and you will get coordinates in x and y. So you'll get rectangular coordinates x, y for corresponding values of the parameter theta, and you can get the same graph by doing it this way. As a last resort, you can also look at this page from your textbook with special polar graphs, and you can see that when you have r is equal to a times cosine theta, you'll get a circle, and the circle will be oriented as you see here in this diagram, which is what we saw for our problem. The diameter of the circle will be a. And we saw with our problem that the diameter of our circle was, in fact, 5. Now we'd like to take a look at Objective 2. You'll be able to convert a rectangular equation into a polar equation. Convert the rectangular equation to polar form and sketch its graph. We have number 28. And these are the coordinate conversion equations. And after you're done with the problem, you should no longer have x and y, but you should have an equation in terms of r and theta. That's what it means to convert the rectangular equation to polar form. So you'd like to use these coordinate conversion equations to make the conversion. So one thing that you notice is that you have x squared plus y squared here, and x squared plus y squared is equal to r squared. And you also have x here, and x is equal to r times cosine theta. So making those substitutions will allow us to no longer have x and y, but have everything in terms of r and theta. So we're going to replace x squared plus y squared with r squared, and then we have minus 2a times x, and x is, of course, r times cosine theta. So we've accomplished our goal of no longer having x and y, but everything is now in terms of r and theta. So we do, in fact, have a polar equation. We like to have r squared isolated, so we'll have to add this quantity to both sides of the equation and get r squared is equal to 2a r times cosine theta. And if possible, we'd like to have r is equal to for our polar equation. So you can divide both sides of this equation by r for r values that are not equal to 0. And if r is equal to 0, then you just have a point at the pole. So for r not equal to 0, we can rewrite this equation as divide both sides of the equation by r. R is equal to, when you divide the left side of the equation by r squared divided by r is r. When you divide the right side of the equation by r divided by r is 1, so you get 2a cosine theta, and that's our polar equation. Now, if you wanted to graph it, there are a couple of ways. You can graph it from the rectangular form, but you would have to complete the square. And we will see how to do that in a later example. But you can also graph it from the polar form, but it's not as easy unless you remember one of the special polar graphs. You can see that our polar equation has the form r is equal to some constant times cosine theta. Our constant happens to be 2a. So we will have a circle oriented as you see here, and the diameter of our circle will be 2a, which means the radius will be a. So this would be These would be the coordinates of the circle in polar coordinates. A, 0. The radius of this particular circle is A, and the diameter is 2A. So we have number 30 here. Convert the rectangular equation to polar form and sketch its graph. So our rectangular equation is x is equal to 10, and if you want to convert that to polar form, you're going to use this coordinate conversion equation. X is equal to r times cosine theta. So you can replace x here with r times cosine theta, and you have r times cosine theta is equal to 10. We like to have r by itself, so we will divide by cosine theta. We'll divide both sides of the equation by cosine theta. So you have r is equal to 10 times 1 over cosine theta, and 1 over cosine theta is secant theta. So you have 10 times secant theta, and that is our polar equation. So we have converted our rectangular equation to polar form. Now to sketch the graph, you're going to sketch the graph based on the rectangular equation because that's really easy to do. So you'll get the same graph regardless, but it's really easy to sketch the graph when your equation is in rectangular form. So there is no y in this equation, it's only x. So y can be any value, but x has to be 10. So we have 5, we have 10, so you have a vertical line for the graph. Number 32, we want to convert this rectangular equation into polar form and then sketch its graph. It's actually easier to sketch the graph from the rectangular equation, so that's what we will do. But if you want to convert this to polar form, you're going to replace x with r cosine theta, and you will replace y with r sine theta using our coordinate conversion equations. So we replace x with r cosine theta, and we replace y with r sine theta, and that's equal to 4. That product is equal to 4. So you have r times r, that's going to be r squared, and then we have sine theta times cosine theta, or you can write cosine theta times sine theta, that's equal to 4. And we can get r squared isolated. You could take the positive and the negative square root, or you can just leave it like this. And that would be your rectangular equation converted to polar form. If you wanted to sketch the graph, it's easier to sketch the graph from the rectangular equation. You can isolate y. Y is equal to 4 over x. And you can make a table of values. Now you'll notice that the function would be undefined when x is equal to 0. But x could be negative. So you can choose some values for x that are negative values. And you can choose some values for x that are positive values. So 4 divided by negative 4 is negative 1. 4 divided by negative 2 is negative 2. 4 divided by negative 1 is negative 4. 4 divided by 1 is 4. 4 divided by 2 is 2. 4 divided by 4 is 1. And if you plot these 6 ordered pairs, you will get a graph as follows. So we have negative 4, negative 1. We have negative 2, negative 2. We have negative 1, negative 4. And we also have 1, 4. We have 2, 2. And we have 4, 1. And in fact, what we get is a hyperbola. And these are the two branches of the hyperbola. There is a vertical asymptote at x is equal to 0. As x approaches 0 from the left of 0, y will approach negative infinity. As x approaches 0 from the right of 0, y will approach positive infinity. There is also a horizontal asymptote, y is equal to 0. As x goes to infinity, y will go to 0. As x goes to negative infinity, y will go to 0. 36. Convert the polar equation to rectangular form and sketch its graph. So this is the third objective for our lesson. You'll be able to convert a polar equation into a rectangular equation. How can we convert this polar equation into a rectangular equation? Well, we see r is equal to negative 2, and we have this coordinate conversion equation, but I can only use that if we have r squared. So what we're going to do is we'll square both sides of this equation, and we're going to have r squared is equal to negative 2 squared, or r squared is equal to 4. And now that we have that, we can go ahead and substitute x squared plus y squared in place of r squared. So we have x squared plus y squared is equal to 4. And we have successfully converted our polar equation to rectangular form. To sketch the graph, it's equally easy to sketch the graph either directly from polar form or from rectangular form. You'll notice that this is the standard equation of a circle centered at the origin with radius of 2. Because you can write 4 as 2 squared. So you can also get the same graph by just starting with the polar equation. So if you have the pole here and the polar axis, and this would be 2 units from the pole, for any angle, there's no theta in this polar equation, so theta can be any angle. You will locate a point that is 2 units away from the pole on the opposite ray from the terminal side of the angle. And the reason why we say the opposite ray from the terminal side of the angle is because r is a negative value, and r is, of course, the directed distance from the pole. But that doesn't really matter, because for any angle, you'll just be finding a point that's 2 units away from the pole regardless. So you'll have a circle with a radius of 2 units centered at the pole. So the graph can be obtained easily from either the polar equation or from the rectangular equation. So now we have number 40, convert the polar equation to rectangular form and sketch its graph. Theta is equal to 5 pi over 6. So to convert this polar equation into rectangular form, you're going to use this coordinate conversion equation. We will begin by taking the tangent of theta. So the tangent of theta, and we know theta, so the tangent of theta is y over x. We're given that theta is 5 pi over 6. We take the tangent of theta, and by this coordinate conversion equation, tangent of whatever theta is y over x. So now we can solve this equation for y by multiplying both sides of the equation by x. And when we do that, we get y is equal to tangent of 5 pi over 6 times x. And what is the tangent of 5 pi over 6? It is the sine of 5 pi over 6 divided by the cosine of 5 pi over 6. The sine of 5 pi over 6 is 1/2. The cosine of 5 pi over 6 is negative square root of 3 over 2. So when you do that division, you'll get negative 1 over square root of 3x. If you want to rationalize the denominator, this is what you will have. So here's our rectangular equation in slope-intercept form. The y-intercept would be 0, so the graph will pass through the origin. It's actually pretty easy to graph this in either polar form or rectangular form. I prefer the polar form. I think it's a little bit easier. So let's go ahead and look at the graph of this polar equation. So here we have the pole and the polar axis, and we begin by determining the angle given by the polar equation. Theta is equal to 5 pi over 6, so we have an angle of rotation that's 5 pi over 6 radians. So here is the terminal side of the angle. And because r is not specified, r could be 0, positive, or negative, so you can have any point on the terminal side of the angle as well as the pole, and as well as points that are on the opposite ray from the terminal side of the angle. So the graph would be the blue line. Number 42, convert the polar equation to rectangular form and sketch its graph. It's easier to sketch this graph after you've converted the polar equation into rectangular form. And how do we convert this polar equation into rectangular form? By using the coordinate conversion formulas that we have. You will remember from trigonometry that cosecant is the reciprocal of sine, so you can write r is equal to 2 times 1 over sine theta. Then you can multiply both sides of the equation by sine theta. You get r sine theta is equal to 2. And of course, r sine theta is y, so you can replace r sine theta with y, and you get the rectangular equation y is equal to 2, which is really easy to graph. It's just the horizontal line where every point has a y coordinate of 2. X can be any value. So here's the graph, and we're done with this problem. We'd like to conclude our lesson for today by looking at number 38, convert the polar equation to rectangular form and sketch its graph. Of course, we've already seen this particular polar equation, and we've already seen the graph of it. The graph is a circle with diameter 5. And earlier in the lesson, we saw how to graph it directly from polar form by making a table of values, or you could turn this polar equation into a set of parametric equations and graph it that way. And now we're going to convert this polar equation into rectangular form, and we will see how we can find that the graph of this polar equation is a circle from the rectangular form by doing something called completing the square. So how do we use these coordinate conversion equations to help us go from our polar equation to a rectangular equation? Well, you'll notice that on the right side of the equation we have cosine theta. If only we had r cosine theta, we could replace that with x. And on the left side of the equation we have r. If only we had r squared, we could replace that with x squared plus y squared. So we're missing a factor of r on each side of the equation, and if we had that factor of r on each side of the equation, we could use these two coordinate conversion equations to convert from our polar equation to a rectangular equation. So we will multiply both sides of our polar equation by r. And because we're multiplying both sides of the polar equation by the same quantity, we maintain equality. So we have the following. So on the left side we now have r squared, and on the right side we have 5 times r cosine theta. And we can replace r squared with x squared plus y squared, and we can replace r cosine theta with x. So we have 5 times r cosine theta, 5 times x. So now we have our rectangular equation. We've actually done what the problem was asking us to do. We've converted our polar equation to rectangular form because we no longer have r and theta, but everything is in terms of x and y. But if we wanted to sketch the graph from the rectangular form, you can rewrite this rectangular equation by completing the square to get it in the form that would allow us to see the center of our circle and the radius of our circle. And here's how we're going to do that. We would like to begin by subtracting 5x from both sides of the equation. That would give us x squared minus 5x plus y squared is equal to 0. We'd like to complete the square here by adding a particular quantity to the left side of the equation, but to maintain equality, we'll have to add the same quantity to the right side of the equation. And to complete the square, you're going to take half of the coefficient of the x term, which would be negative 2.5, and then you'll square that and add it to both sides of the equation. So I'll have plus negative 2.5 squared, and then here I'll have plus negative 2.5 squared. The point of completing the square here is now I have a completed square, and I can write this trinomial as the square of a binomial, and I can write that as x minus 2.5, and of course the minus 2.5 is half of the negative 5, and then I will square that binomial, and then I have plus y squared, and on the right side I have the square of negative 2.5, which is the same as the square of positive 2.5. So when you write your rectangular equation in this form, it has the form x minus h squared plus y minus k squared is equal to r squared. And when you have your rectangular equation in this form, you know that it is a circle. The graph of the rectangular equation is a circle with center at hk and radius equal to r. Radius is equal to r. So for our particular circle, the center will be at 2.5, 0. K is equal to 0 in our particular problem. And the radius would be 2.5. So that's easy to graph. So we're just going to draw our x and y axes. The center of our circle is at 2.50. So if this is 5, then it would be right over here. And the radius of our circle is 2.5. So here is our circle. And we were able to get the graph by first converting our polar equation into rectangular form and then completing the square. Today we looked at graphing polar equations and converting a rectangular equation into polar form and converting a polar equation into a rectangular equation by using the coordinate conversion equations.